So as Roman was just saying, I have been in industry. I'm no longer. But what this talk's going to be about, oh, this is fun, is still an industry experience, but one that I'm doing with a startup in a joint work with a PhD student. So 2 years ago, after over 20 years purely in industry research, I did transition to basic research and teaching here at the HBI in the area of machine learning or artificial intelligence and energy. And what I want to talk about today is a project that we've been doing for a year. It's pretty early on, but maybe it inspires some of the not so obvious, not so deep learning applications of Bayesian optimization. Using the idea of batteries and why they are so important for a sustainable future. And there's a particular problem in batteries, in particular batteries that have large capacities and that have a high energy density. And that's the so-called state of health prediction. I want to then introduce some of the models that are there that model the behavior of an electrochemical battery and show how Bayesian optimization is one of the techniques one can use to actually address this state of health problem of such batteries. I'm also going to give a bit of an outlook on a problem that's specific to this domain, and maybe it's an interesting pattern that one can incorporate in Bayesian optimization generally, and that's, roughly speaking, that of enforcing a functional shape if you do point estimations of an unknown function. And then conclude. So the motivation for my work is really the problem of energy consumption and production. So if we look at worldwide energy consumption, so you see that here since 1965. For those that are interested, there is a stats from BP collected since then, broken down by the sources. You can see that the energy consumption roughly follows the trend of the human population. It keeps going up, and the sources, green and blue, are sources that do not produce CO2, so they're still rather small. For electricity, the picture is a bit better. So for electricity, we have the same functional shape since 85, but we have particularly a bit more of the blue and the green. The blue is hydroelectric, so that's a dam, and green is wind and solar. So this is on the production side. If you look at Germany, it's a little better generally for energy and much better for electricity. So over 50% of our electricity here in Germany comes from renewable sources already. However, one of the key problems of renewable sources is they're really only available in particular days, in particular spaces. So there isn't enough wind everywhere, so that's why you can't place you can't harvest wind energy everywhere. And obviously, when the sun isn't shining, you can't harvest solar energy. So the way to actually make energy available, or electricity in particular, anywhere at any time is to store it. Much like physical products, unless you can't store them, you cannot deliver them quickly at any place at any time. Now, why is that so important? Well, if you look at the CO2 emissions, you can see that while worldwide the CO2 consumption or the CO2 production emissions go up, because of the better mix we have in Germany, it does go down. So in fact, if you normalize the amount of emissions per really large unit of energy produced, so that's in megajoule, you can see that while in the early 60s, when we relied in Germany predominantly on coal, we were above the world average of emissions per unit energy. We're now below. So renewable sources are a solution, but only if you can use them at any place at any time, and that requires batteries. Now, what is a battery? And the general principle of a battery hasn't changed since its discovery 250 years ago. It's basically a system composed of four parts. So the first part is a negative current collector and has an opposite positive current collector. And depending on in which direction energy flows, you either charge or discharge. You call the side that is the positive pole the anode, and the other one the cathode. And these two compartments, they're separated. They have to be separated by a particular material. And as I said, depending on the way that the energy flows, you either charge, so you produce a higher amount of ions on the one side of the battery, on the cathode, or on the anode if you discharge. So that's the general principle. And the problem, in principle, if this was a perfect system, you could charge and discharge any time, but it's based on a chemical process that has side reactions. So if these side reactions happen, the amount of free moving lithium or free lithium ions reduces over time. So that's called the overall capacity or reduction in capacity if the side reaction happens. Now the side reaction is depending on temperature. So there is some known models if we wanted to describe the behavior of those batteries. Now you may wonder, why have batteries only become so important in the last 10, 15 years? And part of the reason is that a battery itself is a device that has a particular weight and a particular CO2 footprint to be produced. And two criteria by which you measure how effective a battery is the so-called energy density, volumetric, when you measure it and normalize it in terms of its volume, so in liters. So this is the amount of energy measured in watt-hours you can put in 1 liter of a battery, or in particular in a weight. And the weight one is important if you want to use the batteries in transportation, because if the battery can't transport itself, you can't put an extra passenger next to it, such in a car. And the volume is important because if the battery is really large, you can't really fit it, for example, in such a watch or in a phone or in something that's usable by human beings. So the more energy you can put per volume or per weight, the more usable for consumer electronics or for consumer devices or for transportation. And in the early days, as you can see, the good old car battery was a lead acid battery. It was rather low energy, a low density of energy. And now we're at the stage of lithium ion, where we've crossed the barrier that the battery is dense enough in its energy density because of the materials used that you can use it for transportation or you can use it in consumer devices, and it lasts long enough. For reference, the numbers there you see go up to 1,000. If you were to use coal or gas, it's got much better energy density. So putting a liter of coal or gas into a barrel is at least 50 times more dense than lithium ion today. However, good news is there's a lot of research happening in material science to increase the density with materials that are more sustainable than burning oil or burning gas. Just for reference, uranium has obviously a huge one, but there's other side effects if this goes wrong. So let's look at this model again. Here's the battery, as I just presented it. And if you want to describe it, you basically describe a time series where the input to the time series, the output to the time series is the voltage you measure and the temperature you measure. Because this reaction of charging, discharging, produces heat, excess heat, and it produces what we want, a flow of a difference in voltage, so a flow of energy. What's the input? The input is the current. So depending, for example, in a car, the amount of charge you apply, the amount of amperes you apply, or the amount of pedal power you apply when you accelerate, that's the negative or positive current that you input into the system. So the cause is the current, and the effect is the temperature and the voltage. However, inside the battery, there is a bunch of parameters that you need to model, and typically in battery modeling, you model the state of charge, so how much of the current capacity from left to right is there, the state of health, how much of the free-moving lithium is still available, and then some parameters of the electrical model. And the electrical model basically gives you a differential forward equation to the state of charge, given the state of charge at time t, and the current that's applied, as well as the total state of health. The model gives you an output, a predictive function that's based on Ohm's law and Kirchhoff's law, on the voltage, and also on the inner parameters of a so-called electrical compatible model. And so that's not everything. I said there is heat produced when the reaction happens, so there's also heat produced when the ambient heat increases or decreases, so when the battery itself is in a different environment. So there is a known differential equation model for given state of charge, given the current, and given the temperature that the battery cell had at time t, what temperature does it have at time t plus 1? And then there is one which is less well understood. It's called the aging model. how big is the site reaction? Because people can't really describe or there's no known functional form yet of the functional dependency of the site reaction with respect to the temperature and the state of charge at time t. But there exist models. So the cause is always the current. The observed time series is always the temperature and the voltage, and the latent variables is the state of health, the state of charge. The state of charge is within charge cycles or discharge cycles. The state of health is what we're after, because obviously we'd like to keep the battery lasting as long as we can. And one way to give you a sense of the time scales, so a typical car battery that we have lasts in its first life. So the first life goes from full capacity to 80% capacity, roughly 5 to 7 years. Because they've only been in the market since 2014, we now talk about a problem where we have beginning to have some early data, ground truth data. If we wanted to have another ground truth data after 10 years, we need to wait 3 more years, and then we have this data available. So what people or what people in this field tend to do is build simulations, because a lot of it's based on physics and chemistry. So the first model we have to build is from a single cell that stores energy to a full pack. To give you a sense again, a car, a powerful car like a Tesla, has about 1,000 cells per pack. A less powerful car can get away with about 50 to 70 cells. But a single cell is not enough to produce enough energy for consumer device or transportation. So you need a model of what's the interaction between voltage and temperature as the battery packs are battery cells are put together in a pack. That's called a battery pack model. Then there's an equivalent circuit model, what I mentioned with the 2 voltages. So this comes from the theory of electricity and describes the behavior of the battery as a device that has capacity and resistance. There is an aging model. That's the one where so far no physical equivalent is fully understood. And then there's a thermal model where basically it's the set of differential equations that describe the heat exchange. The heat exchange from the outside temperature and the heat exchange from the inside temperature that results as a result of the reaction that takes place during charging and discharging. And to give you a sense, so when you want to do research in this field, you don't really wait 3 years to collect ground truth data, but instead you you implement simulators. So this is a typical curve that describes the current as the input, so to speak. So this is a typical charge and discharge cycle. You can see here the resulting voltages that you observe. So blue is the true one that we've collected with the industry partner, and orange is the predicted one. And that's the temperature curves. And as you can already see, our sensory information on the temperature per cell is not as accurate as a simulation with floating point numbers. So the observations are in ranges of, in this case, ½ degrees. The simulated ones are obviously in finer resolutions. So the data that we have when we run a cycle of charge-discharge is the blue curves. The data that we can produce by simulation of the differential equations at fine resolutions is the orange curves. So what we want to do now is really figure out what's the state of health of a battery when it comes out of the first life of a car. So today we have over 15 million cars driving on the streets, and in the next year, roughly speaking, every year there's another 1 million coming into the recycle phase, but not to recycle the battery, but to figure out what's the state of health of every single cell to rearrange them for its second life when it goes from 80 to maybe 60% of capacity in a different form factor. For example, in the construction industry or in the lighting industry or in the media industry. And what we would need is we have this physical simulation, but we don't know what the starting conditions is, because in contrast to the first time that these batteries were used and built in our laptops or in our cars or in our homes, we do not know how degraded every single cell is. So the one parameter that we need to run our simulation, which is the state of health of every single cell, we do not know. And so what do? Well, we have a model that has a number of parameters that we can set by physical equivalence. For example, for each cell that we would like to infer, what's the state of health and the state of charge for each of the cells? What's the initial temperature of the pack when we start to use it? That we can measure. What's the ambient temperature in the room that this takes place? And there are some specific parameters that describe the properties. And what you see on this here is a simulation where we took the simulator to produce the orange curves and then tried to backfit what was the initial start condition, what was the initial state of health, x-axis, that we had used to produce 1 hour of discharge and charge behavior of the battery cell. And if we did a grid search, that'd be expensive, so about 200 trials, you can see that the curve we get, particular notice that we introduced the random noise observation, the discretization, gives you a clear maximum of the log likelihood of observing the orange curve. What you see in blue is running what we did here on a Bayesian optimization to quickly figure out the shape of this, without figuring the full shape of the curve, to find its maximum. And that took only 20 trials, and we did find it. That was a simulation. Then we tried, can this model also be used for a whole pack of batteries? And the smallest pack we built with a startup, it's called Batteries, that we work with, has 14 such cells that are all coming of cars that have been used for 5 years. So cars where the car batteries are no longer usable in the car. And so that's how this battery pack looks. Again, we initialize the state of health of our model. So this is all model-based and backfitting. And then produced a time series of the whole pack and tried to refit what was the individual state of health of every one of these 14 cells. And as you can see, this works pretty well if we have, and the blue crosses show you where the optimizer, the Bayesian optimizer tried to find the best fit for the log likelihood of the whole pack. This works pretty well if our data comes from the simulator. So what we did next, of course, is use actual data where we ran this for, the startup has tried some of these batteries for over a year in various conditions. So it's about 295 charge and discharge cycles, not in a real device, in the lab, where we had access to the temperature. It's about 1 year of time. And if you do that, and for every cycle you run a Bayesian optimization, you get this curve as the curve of the best fit to state of health. And that's a general trend. I think everyone would agree. That's pretty reasonable. It goes down over time, but then there seems to be a high variance. So every single dot is fitting one of these cycles and using Bayesian optimization for figuring out what the initial start condition was, so that the simulator fits the actual observed data. Now the data is actual battery data at the half temperature resolution, at the 30 millivolt resolution of the voltages. And so the observation we made is, while this is a feasible approach in that it captures the general trend, it doesn't incorporate a key parameter, a key property that we know externally, prior knowledge, because a priori we do know that the state of health can never go up. The side reaction always leads to reduction in free-moving lithium because you can't undo it. So that wasn't incorporated. So what we did to remedy this problem without fixing Bayesian optimization algorithms is basically adding a Kalman filter. So what that means is that we use the Bayesian, we assume that we have some non-observable state of health at every single one of the charge cycles, at charge cycle t, t+1, t+2, and that we observed a random sample of it. And that random sample comes out of the Bayesian optimizer, so the observation from BO, the Bayesian optimizer, on all this data of temperature and voltage of every single cell over one charge cycle is the known mean, or you could swap it, the observation at every time step t and t+1 and t+2. But then we added a constraint that the state of health at time t+1 cannot be, is very unlikely to be larger than at time t+2. So you can see that the mean shifts by a multiple of the variance. So kappa determines how much we believe it's monotonically decreasing, how unlikely it is to ever go up. And if you do that, you basically take the Bayesian optimizer as a piece of evidence in a graphical model, a simple Kalman filter, then you do get a much more reasonable estimate of what the actual state of health were, including, of course, the uncertainties at every single one of these 295 time steps. And that's where we currently stand. So this is results from last week. Obviously, there's more work to do because we decouple currently the prior knowledge of monotonicity from the actual Bayesian optimization that runs in sequence. And maybe that's something that can be combined. I'm also at the end of the time, so let me conclude. The first one is, Batteries, hopefully I made a bit of a case that they're a key tool to actually allow us to sustain our usage, our way of living, and our usage of energy over time, because they are the device that decouples the sustainable harvesting of energy with the sustainable consumption of energy. They're also an interesting field of research, in particular when we look at non-homogeneous, so second-life batteries, something that only has ever been as a physical artifact in existence for a couple of years, because they're not well understood. There is, for our research, as researchers, there's interesting questions to be solved. They're also an interesting emerging market when you look at the total amount of capacity that these batteries have. And bear in mind, all these batteries have been built. No more lithium needs to be mined. No more casing needs to be built. If we make them last longer, we have no further bad footprint on this planet. And what we found is that BO, Bayesian optimization, is a really powerful technique to solve these systems of interrelated differential equations. But there is maybe one condition or interesting challenge that's worth thinking about how to incorporate, which is that of, in this particular case, of a functional constraint of monotonicity, because that's prior knowledge we have. You can never get better with a device that degrades over time. Thank you.